Have you ever wondered what happens when the universe presents phenomena that challenge our understanding? Physics is marked by defining moments, and we might be on the verge of another. Currently, an enigmatic object is traversing our solar system, a frosty outsider from the cosmos named 3I Atlas. When astronomers first observed it, most dismissed it as nothing more than another interstellar comet. However, its conduct soon defied all expectations. Instead of following predictable patterns, its glow intensified at odd moments, its movement appeared unusually smooth, and it routinely seemed to evade even the most sophisticated telescopic efforts. These strange behaviors led a Harvard scientist to suggest 3I Atlas might be purposely avoiding observation. Is it possible this is a mere quirk of nature, or could there be intent behind its actions, perhaps from an unseen force between the stars? The arrival of 3I Atlas, noticed in mid-2025 via data from the Asteroid Terrestrial Impact Last Alert System, ATLAS, quickly became one of the era's most talked about astronomical events. Catalogued as the third confirmed interstellar visitor after Oumuamua and 2I/Borisov, it entered our system on a distinctly hyperbolic path, clear evidence that it originated far from our sun. Following its detection, observatories worldwide began targeting the intruder with powerful instruments positioned in Hawaii, Chile, and orbit to elucidate its speed, luminosity, and chemical makeup. Early observations revealed a shimmering coma, signaling active ejection of gases and dust. Unlike inert asteroids, it was dynamic. The comet's brightening and material loss didn't mirror familiar objects. The rate of gas emission was surprisingly uniform despite considerable distance from solar heat, and spectroscopic analysis uncovered peculiar compounds. These surprises energized debate among experts. Some hailed 3I Atlas as perhaps the most untouched specimen from another star system, while others noticed irregularities that didn't align with established explanations. The most compelling sign was the remarkable consistency of its tail, hinting at an influence guiding its emissions. As the data kept flowing in, a Harvard astrophysicist took an unprecedented step, proposing the comet's elusive behavior might be intentional, akin to an artificial entity camouflaging itself. This hypothesis turned routine study into international intrigue. In the weeks after its discovery, the world's leading observatories made 3I Atlas a principal focus. Daily readings tracked its steady emission of water, carbon monoxide, and dust, far beyond what should occur at its solar distance. Spectral observations highlighted unexpected levels of carbon dioxide and complex hydrocarbons, alongside a notable absence of sodium features typically observed in comets. Infrared scans from the James Webb Space Telescope revealed thermal emissions that didn't fit known icy object predictions. The warmth seemed to fluctuate as if regulated. Although subtle, this anomaly ignited new speculation. Researchers adjusted their models to include erratic rotations, stratified interiors, and intermittent gas jets, yet none accounted for all measurements. Compared to typical comets, the surface appeared unusually uniform, with fewer glaring ice patches, and 3I Atlas trajectory deviated slightly from motions governed solely by gravity, as if venting was orchestrated rather than spontaneous. By the end of 2025, radio observations found no incongruous signals, but the optical data stubbornly resisted conventional explanations. Its persistent behavior echoed the earlier mystery of Oumuamua's non-gravitational acceleration, but this time astronomers had richer datasets. The deeper experts probed, the more 3I Atlas seemed to defy the traditional comet profile. This led some specialists to propose evidence of guidance or control. As global space agencies prioritized monitoring the object, one Harvard astrophysicist, renowned for previous claims about Oumuamua, argued that 3I Atlas showed hallmarks of purposeful behavior. His case rested not on science fiction, but on consistent patterns and spectrographic signals suggestive of engineered materials. Though he stopped short of identifying clear artificial origins, he observed the activity, orbital tweaks, and spectral data looked orchestrated. Most scientists remain skeptical, reminding that comet physics is complex, and jetting, dust trails, and sunlight dynamics can easily mimic deliberate changes. Yet even critics admitted 3I Atlas didn't comfortably fit established models. The Harvard scientists proposed the object might utilize volatile compounds to regulate its visibility, and if it truly was a probe or designed structure, it could manipulate its reflectivity to resemble a typical comet. The concept was audacious, and while many found it implausible, it redirected focus back to the physical evidence, suspending preconceptions. This same researcher had previously speculated that Oumuamua's odd motion might stem from an ultra-thin solar sail. With 3I Atlas now displaying similar irregularities, that old debate resurfaced. As a consequence, global scientific teams allocated more time and resources to scrutinize this celestial mystery. The findings produced a wealth of data, radio silence combined with steady thermal anomalies. Whether these signals hinted at technology or a unique natural comet process remained uncertain. Still, the idea of something possibly concealed in plain view captured global imagination. Competing natural explanations soon followed. For every daring theory, numerous grounded ones emerged. Experts in comet chemistry rapidly formulated alternative interpretations for 3I Atlas that didn't rely on assumptions of artificial origin. One possibility proposed that it might be a loosely structured mass of ices originating from a carbon-rich stellar system, chemically distinct from anything found nearby. Its lower density would allow sunlight to penetrate more deeply, generating a consistent release of gas rather than sporadic jets. That could clarify the steady venting patterns. Another explanation cited layered subsurface structures, where volatile ices beneath darker crusts gradually vaporize and maintain smooth emissions. The gentle, continuous push observed might therefore result from equilibrium among subtle gas jets. Some scientists also suggested rotational tumbling, where the nucleus spins in multiple axes, making its motion appear smoother than reality. These interpretations carried weight, aligning with insights gained from 2I/Borisov, which demonstrated that interstellar comets can radically differ from local ones. Borisov's elevated carbon monoxide production and oddly configured dust particles confirmed alien comets could exhibit unexpected chemistries. The same, some argued, could easily apply to 3I Atlas. The disagreement within the field never dismissed science itself. It centered on which hypothesis aligned more accurately with the evidence. As images and measurements accumulated, computer models evolved accordingly, fine-tuning assumptions about gas flow, spin rate, and dust grain behavior. Although none simulated the data flawlessly, several came close. Even skeptics of artificial theories conceded that 3I Atlas defied established expectations of how comets form beyond our solar domain. Natural or engineered, it's reshaping astronomers' perception of what counts as ordinary in interstellar research. The linkage to Oumuamua and 2I/Borisov remains critical. The saga of 3I Atlas cannot be isolated. It builds upon earlier milestones, Oumuamua in 2017 and 2I/Borisov in 2019. Oumuamua, the first known interstellar visitor, puzzled astronomers by accelerating without any visible tail, challenging long-held assumptions about deep space objects. 2 years later, 2I/Borisov appeared as a textbook comet, expelling gas and dust that reassured scientists some interstellar bodies behave like familiar ones. 3I Atlas bridges these two extremes. It displays Borisov's activity, yet mimics Oumuamua's peculiar control-like stability. That duality makes it profoundly intriguing. Reviewing the trio collectively helps scientists refine detection methods and model how materials migrate between star systems. 3I Atlas's steady emissions, contrasting with Borisov's chaotic bursts, suggest it formed under different chemical conditions, perhaps in a cooler region that produced more uniform ices. Or, as some insist, it might represent something far more extraordinary. Unlike Oumuamua, which was mostly observed after it had already passed the Sun, or Borisov, which was studied with limited resources, the reaction to 3I Atlas was remarkably swift. Within mere days, telescopes worldwide were calibrated to monitor it across wavelengths, optical, infrared, and radio, making it the most thoroughly examined interstellar comet ever recorded. Each of these cosmic wanderers contributes to our understanding of the galactic environment surrounding us. Whether purely natural formations or hints of advanced technology, discoveries like C/2025, R2, SWAN, and SOHO enhance our broader perception as 3I Atlas continues to command attention worldwide. At the same time, another comet was brightening nearby, C/2025, R2 SWAN. This luminous object, first identified through the SWAN instrument on the SOHO spacecraft, quickly became a favorite among sky enthusiasts. Although not of interstellar origin, its appearance provided researchers a chance to compare the behavior of a conventional solar system comet with that of the mysterious newcomer. SWAN exhibited the familiar vivid green coma containing diatomic carbon and cyanogen, both of which glow intensely when exposed to sunlight. Its luminosity rose rapidly as it neared the Sun, mirroring the predictable trend most comets display. Astronomers used it as a reference point for calibration before redirecting those same instruments toward 3I Atlas. The difference between them was striking. Swan's emissions followed expected patterns perfectly, while 3I Atlas stubbornly resisted straightforward modeling. Even the peculiar alignment and subtle smoothness of its tail stood out as unusual. Data from a SOHO satellite helped verify Swan's chemical composition and tail configuration, while simultaneous readings provided a baseline to ensure the detectors were functioning properly. In essence, Swan acted as the control sample in one of modern astronomy's most puzzling case studies. To observers with binoculars, it offered a brilliant celestial spectacle, but to scientists, it delivered confirmation that their measurements were sound. Juxtaposing the two comets made the anomalies of 3I Atlas even more pronounced. Its subdued molecular emissions, unwavering gas release, and precise trajectory adjustments appeared extraordinary when viewed alongside Swan's orderly behavior. Swan served as a reminder that most comets adhere to expected dynamics, whereas 3I Atlas remains an exception that challenges those norms. Within academic halls and observatory briefing rooms, debates about 3I Atlas deepened. Teams convened for collaborative analysis, exchanging spectral readings, brightness plots, and thermal scans. The discussions maintained a tone of curiosity tempered by skepticism, as each group sought to uncover the forces shaping its unusual traits. The Harvard astrophysicist who initially proposed that the comet might exhibit controlled motion defended his stance, emphasizing the statistical improbability of certain repeating patterns. His colleagues, however, argued that without tangible proof of engineered construction, it was too soon to draw definitive conclusions. Research teams conducted independent analyses to eliminate any potential observational bias or instrumental interference that might have produced misleading readings. Advanced language models trained on astrophysical datasets were used to recheck thousands of spectral lines in search of hidden anomalies. None showed traces of metallic structures, organized surfaces, or patterned radio signals. However, subtle fluctuations in infrared absorption appeared, hinting at complex organic compounds. These suggested that the comet might contain rich carbon-based chemistry, common in theory, yet possibly more intricate if formed in a distant stellar nursery. As the debate gained momentum, mainstream media amplified the story, often oversimplifying the cautious tone of genuine scientific discussion. Nonetheless, the public attention boosted global interest in interstellar research. Funding priorities shifted, new instruments were designed, and updated analytical software was developed to detect the next such object more rapidly. Rather than dividing scientists, the controversy fueled collaboration. Whether optimistic or skeptical, everyone pursued the same mystery hidden within the luminous wake of 3I Atlas. Beyond the United States, observatories across Europe and Asia began preparing follow-up campaigns. To many agencies, this represented more than an isolated event. It offered a glimpse into the emerging era when ultra-sensitive surveys might spot interstellar objects every few months. The pressure had never been greater for observational astronomy. The pursuit continued as 3I Atlas edged closer to the Sun, with upcoming observations expected to be definitive. Researchers watched keenly for any sharp rise or steadiness in gas output. Either outcome promised to reshape prevailing theories. A surge would support natural sublimation dynamics, but consistent levels could signal deeper complexity. High-resolution imaging arrays were scheduled to measure dust grain distribution, rotational movement, and tail direction, while radio observatories continued to listen for narrowband anomalies. Meanwhile, optical arrays recorded minute changes in brightness with extreme precision. Space agencies were also assessing whether an existing probe might be redirected for a rapid flyby, though such action faced logistical hurdles. The comet's tremendous velocity, over 90,000 kilometers per hour relative to the Sun, and steep trajectory made interception nearly impossible. Even so, simulated mission concepts are underway, exploring robotic interceptors designed to meet future interstellar visitors using earlier alerts. Lessons learned from Oumuamua 2I/Borisov and now 3I Atlas are directly influencing those strategies. Each encounter strengthens the global web of sky monitoring systems, ensuring that next time a traveler from beyond enters our solar system, we will detect it faster. For now, 3I Atlas continues its silent journey, its dim glow persistently tracked by telescopes studying every faint shimmer. The Harvard astrophysicist remains firm in his interpretation, just as his critics remain steadfast in their own. The data itself stays neutral, awaiting understanding. The world keeps observing, realizing that even if this strange visitor is purely natural, it has already transformed how humanity searches for what might not be. The enigma endures, shimmering across the darkness on a path of dust and light. What the future may hold for explorations inspired by 3I Atlas is already unfolding. The comet's reawakening of global curiosity has prompted agencies like NASA and the European Space Agency to reconsider how humanity will monitor future interstellar bodies directly. Both institutions are developing concepts for lightweight interceptor missions capable of launching quickly when a new intruder is spotted. One proposal involves keeping a small spacecraft in standby orbit near Earth, armed with high-velocity propulsion suitable for catching up to such fleeting targets. The objective is to reach an incoming interstellar object within months, before it leaves the inner solar system. Insights from 3I Atlas, particularly regarding its volatile composition and unusual spin, now shape designs for sampling and imaging instruments. Even if intercepting this particular body isn't possible, the data collected is crucial groundwork for future encounters. The idea of interstellar interception has advanced from theory to active mission planning, driven by what 3I Atlas demonstrated. Visitors like these may be far more common than once thought, and each one could hold valuable information about the chemistry and physics shaping other planetary systems. Thank you for watching another episode. While you're here, be sure to check out the video on your screen for more content worth exploring.